better than the originals. So what are we going to do? All right, well, it's time. So welcome back to Supercomputing in Plain English. I've long since forgotten the episode number or the chapter. So we're doing applications and types of parallelism, which is sort of expanding on some of what we learned about MPI, but more importantly, looking at kinds of distributed parallelism. We looked at one kind, and all the usual disclaimers. By the way, I have 107 slides, and we have to be out of here in an hour because there's somebody else who's in the room today. So blah, 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 blah. Thank you. Oh, sorry. Thank you. There we go. Blah, 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 blah. There we go. Okay. So, and we did one last week, which was sort of the classical client server. The Monte Carlo one that we're going to look at today is somewhat less classical client server, but still quite classical in the sense of being what we call embarrassingly parallel. Then we'll look at task parallelism and data parallelism, and look at concrete examples of each. Okay, so let's look at Monte Carlo simulation. So before we do that, a little bit of jargon. We say an application is embarrassingly parallel if the parallelism is super duper in the sense that it's easy to break it up into chunks of however many chunks we want of roughly equal amount of work. And there's hardly any, for example, parallel communication, hardly any overhead associated with doing the parallelism. So we call that embarrassingly parallel, as in an embarrassment of riches. Now, there are some who believe that we should not use a negative word to mean a positive thing, and they would prefer to call it pleasingly parallel. I kind of like embarrassingly parallel. Another term for this is a loosely coupled parallel application, and as we'll see in a little bit, the opposite of loosely coupled, of course, is tightly coupled. All right, and we love embarrassingly parallel applications because their parallel speed up is just about perfect, right? Just about linear on the number of processors. So, here's a picture from Casino Royale, from the first James Bond movie that had, wow, and now I'm blanking on his name, but that guy as James Bond. Anybody remember his name? None of us remember his name. Terrible. Daniel Craig, thank you. All right, good. So Monte Carlo is a city in Europe where they have a lot of gambling. I went to Google Images to look up Monte Carlo, and everything were these opulent, beautiful buildings that were like, they must have cost $1 billion a building or something. They look like palaces, and maybe they were, for all I know. But so what they do in Monte Carlo that Monte Carlo is famous for is gambling. Games of chance are based on randomness. So Monte Carlo methods, which have nothing to do with gambling in this sense, Monte Carlo methods are ways of simulating physical properties using randomness, or otherwise calculating the physical properties. And the advantage of Monte Carlo methods is they are embarrassingly parallel. They typically are incredibly loosely coupled, or they're so loosely coupled there's no coupling at all, and you can just run everything independently. Okay? All right, so here's a classical Monte Carlo method problem, high-energy physics. In high-energy physics, what we like to do is we like to take itty-bitty tiny particles, and we like to bang them together at unbelievably high speed. And every time you bang them together at unbelievably high speed, you get oceans of data. So much so that I believe they discard on the order of 99% of the data that they get every time they bang a couple of particles together at unbelievably high speed. And then they send the remaining 1% or whatever it is out to a whole bunch of places all around the world to do the data analysis. And they also run tons of simulations of banging tiny particles together to see whether the laws of physics that they think govern banging tiny particles together match what they're getting in the data. Okay, so how many ways can you bang two tiny particles together at unbelievably high speed? Is it like 6 or 27 or 1,000,000? Can't slide, but
Just one.
no, there's infinitely many, right? The angles they're coming at and their relative speeds and I don't know what all. But there's infinitely many ways that you can bang two tiny particles together, okay? So can I simulate infinitely many cases? No. And even if I could, would that be useful? Because how long would I have to wait? to get my result. I'd have to wait forever, right? That's no good. I want to know now, right? Okay. So instead of simulating all of them, which is not practical because there's infinitely many, let's choose a subset of them, and we'll simulate that subset and hope that that subset is statistically similar to all of them. Okay? And by the way, I don't mean to each of them individually, I mean to the collection of all of them. The statistics we would get on the subset would more or less match the statistics we get if we actually did do all of them. Okay? So randomly choose a finite subset. The reason we're choosing them randomly is how do we know which one is the right subset to do? We've got no way of knowing, right? Until we actually simulate the thing, we don't know which ones are the ones to simulate. So we're just going to randomly choose a set. Okay? All right. And the idea is that the average of this subset, which is finite in size, a finite number of these that we randomly choose, the average properties of those will roughly match the average properties of the complete collection of infinitely many that we can't possibly do. So for example, a way to do this, and this is pretty common, is you just keep doing them until doing more of them doesn't change the results, doesn't change the statistics you're getting, right? So I start and I do one, and then the next one is different, and then the next one is different from that. But over time, as I do more and more of them, they sort of start to converge to somewhere. And when doing more of them doesn't change where they're converging to anymore, then I stop, right? I'm vastly oversimplifying, of course, but to first order, that's roughly how we're going to do that. Now, the other way we can do that is if we understand the math really well, we can calculate how many we need. We can say, oh, we need to do 1 billion randomly generated, what we call realizations of this phenomenon. And if we do 1 billion of them, then that will give us the level of convergence we need. We'll be within whatever epsilon or whatever that we decide we want to be within. Okay. I suspect it's more common that you just keep going until it converges than that you know how many to do to get to a particular level of convergence. But I couldn't prove that. I don't know that that's true. Okay. So the great thing about Monte Carlo is it's embarrassingly parallel because the only interaction among these zillion randomly generated realizations are A, making sure that the random number is not the same on all of them. Because if you do like 8,000 cases that are all identical, that doesn't help. It messes up your statistics. And B, collating the data together at some point, whether it's occasionally, for example, to check for convergence, or if it's just at the end because you knew how many you needed, but from time to time, you're going to have to do some kind of collation step. And so that's really, the collation is really where the only parallel overhead is. There are random number generators, parallel random number generators that will make sure that your random numbers don't overlap. Okay, so you don't have to panic about that. All right, so remind me, we're the Fortran people in this room or we're the C people? We're the Fortran people, okay. So I'll do the Fortran version then. Okay, so here's the Fortran version, right? So we read whatever the input is, and then we loop over however many realizations we're doing. This is the I know how many to do. The I don't know how many to do, I'm going to keep checking. You do it as a while loop or whatever. Okay. So I generate a realization and I calculate its properties. And I do that a zillion times, and then I calculate the average. Right? Now, in real life, it's quite likely that calculate the average would come up into the loop and be calculate some kind of running average, because then you don't have to hold all the data in memory, because if you're going to do 1 billion of them, holding all of that in memory or even on disk may be a bit much, but you're either doing it at the end or you could be doing it on a kind of ongoing basis or something in between where you sort of calculate a running average from time to time, whatever it is that you do. Okay, so that's good. All right, so how do we parallelize that? And let's do this with MPI because we love MPI. By the way, do we love MPI or do we hate MPI? How many of you love MPI? Hate MPI? Both at the same time. Okay, so why do you hate and love MPI at the same time?
I mean, it takes time to rewrite the code.
Yeah, oh, it's a pain to rewrite the code. And it's worse than it takes time, because that would be true with OpenMP or whatever. The problem with MPI is it's incredibly clunky. It's really ugly, and you have to do so much stuff by hand. It's a real pain to write the code, right? But the advantage of MPI is that you have so little incentive or so much negative incentive to do things like communication that you get to be really, really careful about that stuff. And you think carefully about it. Where in OpenMP, you don't spend a lot of time thinking about, oh, I'll just parallelize this loop, ooh, yay, right? Here you have to think carefully, and thinking carefully actually gives you typically a better outcome. All right, anyway, so I do my MPI startup, right? We remember we call MPI init and so on. Com size, com rank. Okay, so if I'm the server, then I'll read the input, then I'll broadcast all of that out to everybody, and then everybody's going to do their thing. But notice now I can do, instead of doing from 0 to however many realizations, now I can do from, oh, that's the C version, from 0 to number of realizations divided by number of processes. So each process is going to do roughly an equal number of realizations. Now, of course, I've oversimplified all this, right? Of course, that's true. But it gets the basic idea. All right, so, and here, I generate the random realization, I calculate its properties, and then I can calculate a running average locally for my subset. And then when we're all done, then we can share that around to calculate a global average, right? We'll do some kind of sending and receiving. Okay. Oh, and do I have a picture? Oh, that's the Fortran version, right? Same idea. Okay, I don't really have a picture beyond that. All right, so that was it. So isn't this nice? So this is, again, I've wildly oversimplified this. But to first order, this is basically all you have to do, right? Now, again, in real life, it's always going to be more complicated. But this gives you the basic structure of the thing. And so here, what we'd be doing is, we'd be doing like a reduce or something, right? We'd add them up and then, divide by how many there are, whatever, right? Whatever it is we're trying to do. We would do some kind of communication in here to make sure that everybody ends up, or that process 0 at least, the server, ends up with the right answer, which we can then output or have to. Right? Pretty straightforward. All right, so now we'll get to the next one, which is task parallelism. And in our last episode, we talked mostly about what we call point-to-point communication. So we were looking mostly at MPI send and MPI receive. So MPI send comes from a particular MPI process, MPI rank, and goes to a specific MPI process, MPI rank. So you have a source process and a destination process. Whereas with collective communication, there might be one sending and everybody receiving, or there might be one and everybody sending, or it might be that everybody is sending and everybody is receiving, right? But everybody, for collective communication, everybody calls the same routine at the same time, and in fact, you can't get past that routine until everybody has called that routine. Okay, now, an n-body problem. So an n-body problem is, you will be shocked to learn, a problem with n bodies, okay? So here are n bodies. I didn't count how many, right? All right. So the two sort of classical n-body problems are stars and atoms, okay? So let's say that we have a bunch of stars. So I'm a star. Oops, I just tapped my microphone. I'm a star. You're a star. You're a star. You're a star. You're a star. Everybody in the room is a star, right? So if I'm a star, do I exert a force of gravity on you? I certainly do. Do I exert a force of gravity on you? How about you? You. Do I exert a force of gravity on each and every one of you in the room? And in fact, in the universe, right? I exert a force of gravity on each and every one of you. Now, the ones that are really far away, that the amount of gravity that I exert on them is real close to 0. But let's just think of it as now, do you exert a force of gravity on me? How about on him? And her, him? Absolutely. So each one of us exerts a force of gravity on all the others, right? So if there are n of us, then each one of us exerts n-1 forces. And the total number of forces for all of us is n times n-1. So far, so good? All right. Now, if n is 1, this is super simple, right? Because if there's only one body in your universe, then who can exert a force on them? Nobody, right? So there's no forces on them. All right. By the way, physicists, pretend that anything I'm saying is true. I realize everything I'm saying is wildly oversimplified and therefore applies. But, so if I know the position and velocity of the one particle, the one star, at a particular time, let's call it t0, then I can perfectly calculate its position and velocity at any time in the future, because its velocity at any time in the future will stay the same, right? So momentum, is that the right word, physics person? Okay. And then the position will change in a very simple way, right? I'll move by velocity times delta t for whatever the delta t is, right? Very straightforward. Again, I recognize it's full of lies, but to first order, right? Now, let's make this worse. Suppose I have two bodies. So my two-body problem, each one of them is exerting some force on the other one, right? So in the case of stars, if I have two stars, each one of them is exerting gravity on the other one. In fact, the amount of gravity they're exerting is equal, just in the opposite direction, right? Okay. So it turns out that a two-body problem, there's a nice, I guess it's a differential equation, and you can do the appropriate stuff that we learned in sophomore level differential equations or whatever, where you do the appropriate transformation and you get a lovely closed form solution, so you always know the position and velocity of both particles. Very straightforward, right? That's the last time that's going to happen, okay? So now a three-body problem. So each particle has two forces coming in and two forces going out, right? So far so good? Okay. So it turns out that there is a closed form solution. It was discovered 106 years ago by a guy named Sundman. I forgot what Scandinavian country he was from, but from some Scandinavian country. Now, if you go look this up on Wikipedia, they talk about him. Anyway, it turns out there is a closed form solution for a three-body problem. But that closed form solution is expressed as an infinite series. And it turns out that the infinite series is so long in order to get a reasonable convergence on positions and velocities that it's wildly impractical to use in real life and nobody does. Okay. So what we then have to do is move to the general n-body problem, so for n greater than 3. And for the longest time, it was thought that there probably was not going to be a closed form solution for the general n-body problem. And then, what is it now, 27 years ago now? Qidong Wang, who, I can't remember what university. Anyway, mathematician, figured it out. And I actually even have the reference. You can go look up the original paper. It's on the web. A closed form solution for the general n-body problem for any n greater than 2. I believe this also does apply to 3. In any case, doesn't matter. So, but again, the same problem. The closed form solution is again an infinite series. And I actually stumbled on the web onto a claim, and I don't know how to verify it, so I don't know if it's really true, but they claimed that the number of terms you have to calculate in order to get a reasonably accurate answer, the number of terms you have to calculate is 10 to the 8 millionth power. Okay, good. Thank you for making that disgust noise, because that's exactly the correct answer. So that is a perfectly good answer mathematically, but totally useless in real life. Okay, so nobody does that because, you know, we aren't made of time. Because time is money, that's correct, and we're not made of money. All right, so nobody uses the closed form infinite series because it's ridiculously impractical in real life. So instead, what you do is you actually calculate the forces between the particles, right? And it turns out that's pretty straightforward to do, both for stars and for atoms. There are well-known formulas that describe the forces that you're impinging from one to the next, right? From any particle to any other particle. It's all very well understood. You can open up any textbook, and well, not any textbook. You can trivially go on the web and find this stuff. It's very straightforward. I even wrote a little code that I stole from a book and then sort of modified to make it more readable that I have available if somebody wants to borrow it. And it's very straightforward stuff. Now, here's the challenge. So the challenge is when you've got n bodies and you've got n times n minus 1 forces, that's an enormous amount of calculation to do. So much so, by the way, that it's job security for people in the supercomputing business, right? This guarantees us that we can't be laid off, right? You can be fired for cause, but you'll never be laid off because people have to do n-body simulations. So it's roughly n squared forces. So here's my n bodies, right? And you can see there's a force and there's a force, right? That's why I don't really have 107 slides. It's kind of a lot. All right. So, and by the way, n times n minus 1, that's slightly a lie, because it's really n times n minus 1 divided by 2, because the force from me to you and the force from you to me is the same, except for the direction, right? It's in the opposite direction. It's change the sign, roughly speaking, and we get the other force. All right, so, so far, this is how many forces we have to calculate, right? So I'm going to take a moment and have kind of an aside, kind of an interlude, to talk about a concept that computer scientists all learn when they are wee lads and lasses in undergrad, and that stays with you, but kind of ignores the whole issue of performance. All right, so this is what we're working our way up to is what's called big O notation. So let's say you want to do some task, and that task has a number of pieces, a number of subtasks to do that can be expressed as a polynomial, or the time it takes to do that task can be expressed as a polynomial, right? So constant constant k times n to the k power plus constant k minus 1 times n to the k minus 1 power all the way down, right? Okay. So for example, let's say that I want to settle into my easy chair and read a lovely book, right? Well, so there's a constant that I have to apply to settle into my easy chair with my smoking jacket and my slippers and my snifter of brandy, right? So I hope not putting into your head a picture of somebody who has a lot more money than I do, okay? And then once I've settled into my chair, then it takes me, let's say, a certain amount of time per page to read the book, right? So the total amount of time is the time it takes me to settle into my easy chair with my snifter of brandy and some constant times the number of pages of the book, right? That's the total time I'll spend reading that book in my easy chair. And here's the thing. If the book is actually a pamphlet and it's just two sides of a piece of paper, then it might be that the time it takes me to settle into my easy chair and swirl my brandy of snifter, my snifter of brandy, excuse me, that total time might be bigger than the time it takes to read the pamphlet. But once I open a real book with a lot of pages, then the time it takes me to settle into the easy chair is basically zero. It's meaningless. What's important is the time I spend reading the pages, right? If I'm reading this thick tome, it's going to be, page after page after page. It's going to take me a long time. It's nothing to do with the time it took me to settle into the easy chair. So in that case, for large n, I can ignore the smaller term, right? And in fact, if the largest term is n squared, I can ignore the n term and the constant term. If the largest term is n to the 80th, then I can ignore the n to the 79th, the n to the 78th, and so on terms down to the constant term. The constant term being n to the 0th. Right? All right. So because of that, because as n gets large, right? So think of, let's do n cubed, right? So if it's constant 3 times n cubed plus constant 2 times n squared plus constant 1 times n plus constant 0 times n to the 0. If it's that, well, at a million cubed is, let's see here, quintillion, whereas a million squared is a mere quadrillion. Trillion, right? And a trillion is a tiny fraction. It's surprisingly 1/1,000,000th of a quintillion. So it's irrelevant, right? It's round off error, let alone the thing that's actually a million. So I've got a quintillion, a trillion, a million, and a constant, right? The only one that matters is the quintillion, whatever the constant is. Doesn't matter what the constant is. For a large enough n, the constant becomes irrelevant. And what matters is only the big term is going to contribute to the total amount of time, right? So we indicate this in the computer science world with a big capital O being order of. So on the order of n or n squared or n cubed or whatever. And there are other things than that. So for example, you can have on the order of log n, but we're not going to get into that. Okay. All right. So an n-body problem is big O of n squared calculations versus big O of n data. That is, you have n particles. Each of the particles has some, it's got a mass and it's got a velocity, which is a 3 vector, right? and it's got a position, which is also a 3-vector. I think that's all you need, isn't it? Mass, velocity, position. And you know how much gravity it's going to exert, and then you can start moving it around, right? So you're looking at, what was that, 7 8-byte quantities if we're doing double precision. So 56 bytes, is that right? 56 bytes per, right? So 56 bytes times n for the number per. But the number of forces we calculate is n times n minus 1 over 2, right? So first of all, the over 2 goes away because we don't really care about that. And the n times n minus 1, which is really n squared minus n, the minus n goes away, right? Really all that matters is the n squared. So we say it has order n spatial complexity, how much RAM it consumes, or how much storage, and order n squared temporal complexity, how much time it consumes. Right? Now, the reason we don't care about the constant is that, I'll use a picture of that. The reason we don't care about the constant is that computers are always changing speed anyway. So whatever the speed is right now on this computer, you know, next year you're going to buy a computer that's faster than that. And so what won't matter is the actual speed. What will matter is how much more time it takes if you make n bigger. Okay, so here's a picture of the forces. I've only drawn n of them, by the way, or n minus 1 of them. If I drew all of them, this would just be like a big sort of black mass here. It wouldn't really show you anything. Okay. All right, so how do we calculate? So this is more or less, again, physicists don't correct me. This is more or less how you calculate it at stars, right? Here's the gravitational constant, here's the mass of the 2 particles, here's the square of the distance between them, right? And that's more or less the force between the 2 particles, right? Okay, great. All right, so, and then you calculate these order n squared forces. All right, so you got order of n squared forces. How are you going to parallelize that? We have 4 ways we can do it. So we can think of this as a client-server thing, right? So we have a server, and the server sends out, let's say, particles to the various client processes, and then they do their work, send the results back to the server. Or we have a server, and the server sends out interactions, pairs of particles, to the client processes, and they do the calculations and send the results back. Or, no client, no server. Have every process decide its subset of either the data or the work. So we could have, each process says, I have a particular subset of particles, and I'm going to share them around and then I'll share around the summed forces on those particles. Or each process could decide its own subset of the interactions, okay? And then calculate the summed forces for those interactions and share those around. So the question becomes, how do we decide which one to do? Right? I've already come up with 4 ways to do this. How do we decide which one? Well, let's think carefully about this. First question is, do we need a server? Right? Do we need somebody feeding data to the others? Right? Well, you're going to be calculating these interactions. So in order to calculate the interactions between any 2 particles, what do I need to know about the 2 particles? Physics person.
Yes.
I need to know the mass of each. Yes, what else? The distance. So, where'd that go? I had that thing. Yes. And I need the gravitational constant, but that's just a constant, so that's easy. Right? So I need the masses and I need the distance. So to get the distance, I need the positions. Right? All right, good. So, and I'm going to do this a zillion times as I move these particles around, right? Okay. So do I need a server? Well, the question then is, can each of these processes decide for themselves which subset of the work to do? Is there a way to calculate who's going to do what? If you can have each process figured out for themselves, then you don't need a server, right? Then you get rid of the client-server part. Okay. All right. Well, you then have to answer the question, are we going to parallelize it by the bodies, in this case the stars, or are we going to parallelize it by the interactions? Oops. Right. Okay. So this leads us to some jargon. Data parallelism versus task parallelism. Data parallelism, I take the set of data. Yes, question from TV Land.
Is the reason we don't similar to the concepts of weak, strong scaling that we discussed a few weeks ago.
Good. Is the reason we don't care about speed because of the issue of weak versus strong scaling? No. And I should be careful about who it is who doesn't care about speed. How many of you care about speed and you bother to show up here because you care about speed? Okay. How many of you, speed is irrelevant? So here's a conversation I once had with a computer science colleague of mine. I was bemoaning the fact that computer scientists don't care about performance. And my colleague said, that's not true at all. We care a lot about performance. We start from sophomore year teaching performance. I said, what are you talking about? And she said, no, we do big O. I said, no. That's not performance. That's complexity. Performance is the constant. She said, oh, no, yeah, we don't care about that. Right? So we care deeply about performance, but computer scientists do not. Because from the perspective of computer scientists, the constant, that's going to change every year anyway as new computers come out. But from the perspective of scientists and engineers, from STEM research perspective, we just want to get our result, right? And we want to get it as quickly as possible so we can get the next result. We can publish more papers or sell more products or whatever it is. So we care deeply about the constant. The computer scientists don't care about the constant. However, it helps us to understand conceptually if we think about these things from a big O perspective. Okay, now, data parallelism versus task parallelism. Data parallelism, I take the collection of data, I split it up into subsets, chunks. I give a subset to each of the processes, and then each one of them does their own stuff on its subset of data. Task parallelism. I take the list of tasks to do, I split that up by the set of processes, and each process gets a subset of tasks to do. Typically, in data parallelism, all of these subsets of data get at least roughly the same list of tasks done to them. And in task parallelism, all the subsets of tasks are applied to the entire collection of data. That's not always true, but it's often true. It's quite typical. Okay. So is there another question for TV Land?
So does this tie into weak, strong scaling then? What is the difference?
It does not directly tie into weak versus strong scaling. Strong scaling means I run the same size problem on more processes, and hopefully it takes less time. Ideally, it goes down linearly with the number of processes. Weak scaling means I run a problem size proportional to the number of processes, and hopefully it takes about the same amount of time as a smaller problem on proportionally fewer processes. And in my experience, weak scaling is more important than strong scaling, ironically. Okay, so data parallelism. We could do data parallelism. So take the list of particles and split them up, right? But then you'd have this problem. So, let's say you've got particles 1, 2, 3, and 4 over on process 0, right? So, well, what happens then? You can calculate the forces between 1 and 2, 1 and 3, 1 and 4, 2 and 3, 2 and 4, 3 and 4. But you can't calculate, for example, the force from any of those to 5. But you do need the force between each of those and 5. So the only way you're going to get that, because 5 lives on another process, is for that other process to send the information about 5 to process 0 every bloody time step. And you're going to do like a million or a billion time steps, right? You're simulating a galaxy over, years, decades, millennia, epochs, right? So, right, physicist? Yes, good. All right, so, see, I keep going back to you because you actually know this stuff and I do not. So, all right, so the problem then is if you split up by data, still constantly, to calculate the forces, you're constantly communicating. So is data parallelism a good approach? Data parallelism gives you a very high communication cost every single time step. That's no good. We don't want that. All right. So how about task parallelism? So everybody gets the full collection of particles, right? I have 1,000 particles, and each process gets a copy. And then each process does a subset of the force calculations. And then at the end of that, you do some kind of sharing of your sum of those forces that you got locally on your process with all the other processes, and you get a global sum of all the forces. That sounds pretty good. Because now the only communication you do is sharing the local sums of forces. Because you calculate the sum of forces, right? On process 0, calculates the sum of forces. Process 1 calculates its subset of the forces and the sum of them. Process 2, process 3, and so on. Each one of them calculates some. No communication in any of that. Right? Then when you've completely done all your calculations, then we all share with a collective communication. Right? There's a number of ways you can do that. So, communication cost of doing task parallelism, not literally 0, much, much lower. That makes us very happy. Okay. Now, and I mentioned, so one of the ways you can do this is each one has their local sum of the forces, and then you do a global reduction. Okay. So here's reduce. Okay. So this is a collective communication. So everybody calls exactly this call. So here, the way we might do it is we have our local sum of forces. Right? All the forces we calculated locally, okay? We're going to sum that into a global equivalent. And this is how many particles we have, because every particle has its own sum of forces that impinge on it, right? This is the data type. This is the operation we're doing. We're taking the sum. Okay? This is who's getting the answer, right? The rest of the processes don't get the answer, just this one. And then here's our MPI communicator that we decided to pretend we don't want to deal with much. Here's the Fortran version, right? It's the same idea. Okay. Yay. Okay, now, here's the problem with that. After everybody has calculated their local subset of forces, we need to get a sum of all the forces that impinge on each and every process, right? Well, if only process 0 gets that sum, but everybody needs to move the particles around, what process 0 could do is process 0 could then calculate the movement of the particles, right? Calculate the change of velocity and position of every particle based on the forces, sum of forces, and then, this would be nice, broadcast all of that out to everybody. But there's a cheaper way to do it, which is we could send the result of summing those forces to everybody, and then they can themselves locally calculate the new positions and velocities, because they'll all get the same answer, but the communication will be cheaper. Because all you'll be sending is a force free vector, instead of sending position, velocity, and mass. Well, I guess you don't have to send mass, but position and velocity. You cut the amount of data you're sending in half. Now, you are doing redundant calculation. Every process is doing the exact same calculation for moving the particles around, for changing the positions and velocities. Every process is doing that calculation for all of the particles, not for a few, for all of them. But it takes only order n calculations to change the positions and velocities. So the amount of calculation you do to change the positions and velocities compared to n squared force calculation is basically 0. It's not literally 0. It's basically 0. So what you end up with is if everybody calculates their own copy of the positions and velocities, they do redundant calculation. Everybody's doing the exact same calculation. But the cost of doing that is almost 0. So you might as well. It's cheap, right? You're not really spending hardly any money, right? You just spent $1 million to calculate the forces, and now you're going to spend 10 cents to calculate the new positions and velocities. That's worthwhile. Particularly because if you double the cost of the communication, sending twice as much data, that's going to be more than 10 cents. That might be $10. Okay, so here's all reduce. All reduce is essentially identical, except we got rid of who it's being sent to. Right? So everybody gets it. Now, all reduce typically takes longer, but not much longer. Okay. There's the Fortran version. Looks pretty much the same. Okay. So collective communications, reduce and all reduce we were just talking about. There are others, broadcast, gather, scatter, all to all. This is not an exhaustive list, but it kind of gives you the basic. I may talk a little about them. So collectives are expensive. When you look at the bandwidth of a collective communication compared to a point-to-point from one process to another communication, the bandwidth is much lower. The amount of data you move per second is much lower. But if you compare the cost of doing a collective communication to accomplishing the exact same thing using point-to-point communication, send and receive, it's much, much cheaper. And the rule that governs that is at any moment, any process, and that's actually not quite true, inside the computer, inside the server PC, that's your computer, inside of there you have a card for the network, right? Or if you're super lucky, it's built into the motherboard, but usually it's a drop-in card. Okay? That drop-in card typically has 1 or 2 ports, depending on how much money you have to spend. We usually will not spend enough to buy more than 1 expensive network port per server. Okay? That port can be doing one thing at a time, essentially. So it can be sending a message or receiving a message at any given moment. And only one. Now, again, I'm vastly oversimplifying. Everything I'm telling you is a lie, but it's close enough to the truth conceptually. So if I want to have all of us know something, so I know a thing, and I want everybody to know this thing. And remember, the rule is I can talk to any one of you, and I can either be sending or I can be receiving, not both at the same time. And I can only talk to one of you at a time. Okay? So here's what I'm going to do. I'm going to send a message to Jim. Okay? Now, then while I send a message to Jim is going to send a message to Debbie. And then the 3 of us are each going to send a message to one of the others. Right? So in 3 steps, we get all of the information to everyone. So instead of me going, Jim, Chow, Debbie, instead of me going to each of you individually, I can go to one of you, and then while I'm talking to the next of you, they're talking to one of you. And then the 3 of us, actually the 4 of us, excuse me, are talking to 4 other people, and so on and so on. This is sometimes called butterfly communication. When you draw it, it looks like a butterfly. But let's not worry about that. So, in other words, even though collectives are slow by sort of conventional metrics, they are super fast compared to doing it as a series of point-to-point communication. Okay? Good. How are we doing on time, Debbie?
We have, it's 15:15.
Okay, so we got 15 minutes. Okay, so that should be enough time.
Get ready.
All right, so let's do data parallelism using what's called a transport problem. Okay, so transport problem, the most common kinds of transport problems, at least that we see here at OU, are what are sometimes called computational fluid dynamics. Here, fluid does not mean the same as liquid. Fluid in this context means liquid or gas, right? And usually, more often than not, it's a gas. In this context, so not like drink plenty of fluids like people tell you when you've got a cold. Fluid there means liquid. Here, it means liquid or gas. And so, for example, here at OU, we have people doing lots of weather forecasting. So the gas that they're doing is the nitrogen oxygen atmosphere, rolling around above the ground. Okay, so we're clouds and rain and snow and stuff live. Okay, so other than the simplest, least interesting cases, typically these kinds of equations that represent transport physics cannot be represented in closed form, right? There's no closed form solution, so therefore we have to do a numerical approximation, right? Which is, I think, what a lot of folks who use supercomputers use. Now, of course, bioinformatics, data mining, that kind of stuff is a different character, but let's go back and remember in the distant mists of time when we took Calculus 1. How many of you remember Calculus 1? No. So Calculus 1, they said, I want to find the area under the curve, right? So this is the integral calculus. Maybe that was Calculus 2, depending on how your semesters were broken up. Yeah, I want to find the area under the curve. Right? And they taught us this thing called Riemann or Riemann, I think it's Riemann. Riemann sums. So you pick points, and typically they're equally spaced, so they don't have to be. Pick a bunch of equally spaced points, put a line through it, turn that into a little rectangle. Calculate the size of the rectangles, sum them up, that gives you, well, does that give you the area under the curve? How many of you vote yes, that gives you the area under the curve? No, that does not give the area under the curve. It depends what you mean by the area under the curve. So it gives you not the actual area under the curve. This is a famous painting by a guy named Rene Magritte. Ceci n'est pas une pipe. I'm sure I pronounced that horribly, but that means this is not a pipe. Right? Is this a pipe? How many of you vote this is a pipe? This is not a pipe. This is a representation of a pipe, but not the actual pipe itself. Right? Yeah. So that's what the sort of the joke is, right? It's a picture of a pipe. That doesn't make it a pipe. Okay. So this is an approximation of the area under the curve, but it's not the actual area under the curve, right? Okay. Well, what if I cut the width of all of my rectangles in half and I double the number of rectangles? Is that better or worse? Okay, how many of you vote better? How many of you vote worse? How many of you vote it depends what you mean by better and worse? Okay, is it more accurate? Yes. Is it faster or slower to calculate? Oh, and what is time? Time is money, right? So it's better and worse. It's better in terms of accuracy, it's worse in terms of calculation time. Okay? Now, if we had, I'll try and use the correct calculus terminology, arbitrarily many such rectangles, and each one of them was arbitrarily thin, right? Then in the limit, we would get the integral, which is in fact the area under the curve. Right? That's what all it's about. That's what the integral sign means. It's a big S, right? All right. So then that kind of is the pipe. That is, it is the area under the curve. So it turns out lots of physics problems, and physics, by the way, when I say physics, I don't mean physics, science problems. Lots of problems that use physical laws, those physical laws are described by differential equations, right? So differential equation is an equation where differentials like dx appear as terms in the equation. Okay? So lots and lots of stuff is expressed as differential equations. Almost no differential equations, and certainly not the interesting ones. The interesting ones typically cannot be expressed in closed form. So you have to do a numerical approximation, right? By the way, how many of you do numerical approximations? Okay. How many do numerical approximations of transport of, for example, the Navier-Stokes equation? Okay, good. So you'll fit right in. Good. All right. So you start with a mesh, right? Some kind of lattice, some kind of grid. I'm going to use the word mesh for the most part. Okay. And then you calculate the values, for example, in the center of the mesh. Again, wildly oversimplifying, but to first order, this is close enough. So here's a picture of this. This is actual weather data that I stole off the Center for Analysis and Prediction of Storms website years ago now. And so, right, we got it. Now, by the way, of course, in real life, the grid, the mesh is much finer than this, right? With little tiny squares. But this kind of captures the idea. You get, and so the data lives, say, at the center of that little rectangle, right? Then you take your differential equation and you replace it with a difference equation. You use finite difference. So instead of having dx, which is infinitesimally thin, you have delta x, which actually has a finite non-zero width. Okay? Likewise, dt instead of delta t instead of dt. So here's the differential equation. Here's the difference equation, finite difference. And this is exact, but we can't calculate it. And this is approximate, and we can't calculate it. Okay? Now, don't get too frightened by all the formulas. They're not there. They're only there to frighten you. Okay. So what we do is that we take our standard Cartesian coordinate system. By the way, it doesn't have to be Cartesian, but let's just use that for simplicity. Okay. And we construct a mesh in 3D where the data lives. So here, for example, U would be the east-west version component of velocity. You can do that in Fortran or C, doesn't really matter, right? And you'd have a bunch of these for the different variables, UV, P for pressure, I don't know what else, D for density, whatever the heck it might be, right? Whatever you're calculating. You have a nice 3D mesh. And the way you calculate it is, at any particular position in that mesh, the value at time t plus delta t is the value at time t of, let's see if he's there somewhere, me and my immediate neighbors, right? And what that function is can be very, very complicated, but to first order, it's some function of those. If I were to super oversimplify, let's just say take the average of them. In real life, nobody does that, but to give you some idea, right? Okay. So very straightforward then to go forward in time by delta t. And again, I'm massively oversimplifying this. There's way more complexity than anything I'm talking about. And it may not just be your immediate neighbors around you, they could be a few squares away from you, right? It might be a much bigger footprint than that. Okay. Well, if you're going to do that, then you have this problem that to calculate the value here, right on the edge, or over here on the edge, you need something next to it that is not being calculated each time step, at least not in that sense. Right? Now, sometimes it is. You might have, for example, this might be the same as this, or the same as this in the opposite direction, or you might have some periodic boundary condition where this here has the value of this here, right? Or you might have something more sophisticated than that, or less. But you have some way of filling in those ghost boundaries, right? So then, once we have that, we can straightforwardly do the calculation that I just showed, right? We have enough neighbors that even on the edges, we can get the calculation. So far, so good? So here's a picture of how this gets done. That's the C version. I think I have a Fortran version. Yeah, there we go. So we loop over the time steps, and in each time step, we fill up the ghost boundary zones, however it is that we do that. And then we do whatever it is that we do to apply the physical laws that govern that transport process. So let's say it's the Navier-Stokes equations that I showed you earlier. It could be anything, but the first order is that. And this works great on one process. Now I want to speed that up. I mentioned data parallelism. So what we're going to do is we're going to take this giant thing and we'll split it up into chunks. We'll split it up into subdomains, they're sometimes referred to as, or subregions, or patches, or tiles. All these words are used more or less interchangeably. And we'll give one of those to each of the processes. Now, by the way, we could give multiple of those to each of the processes. I'll talk about that next time, I think next time. All right, so here's how we decompose the data. So this is a very simple way to do it, right? We just split it up into chunks of equal size. We give a chunk to each of the processes. Very straightforward. Now, it might not perfectly divide, right? You might have a few extra mesh zones on process 12 or whatever, but that doesn't matter. It's close enough. Now, it turns out MPI provides a way to do that in Cartesian coordinates so that MPI can figure out which processes should live next to which other processes in order to minimize the cost of communication. So, for example, it might be advantageous for this process, for this chunk to be on process 12 and this chunk to be on process 13. And the reason that might be advantageous, you can see stuff is going to flow from one to the other. It might be advantageous to have them on processes 12 and 13 if processes 12 and 13 lived on the same server computer, because then they could exchange their data without going out to the net. So by using MPI cart create and this other stuff, okay, we can let MPI decide for us how to lay out the data, because MPI is more likely to know the structure of the machine than we are. Okay? So let MPI do that thinking for us. Okay? And that creates a new communicator. And so you stop using MPI Common World and you start using this new communicator that has laid the data out properly. And I'm not going to go into the details of that. You can look that up on the web. But it's set up specifically to help with this kind of problem. Okay? So now you can do MPI receive and MPI send so that we can exchange data. Oops, let's go back to that picture. So process 12 and process 13 can exchange data along this boundary here. Right? Rest of it? This gets us to a weird property of MPI send and MPI receive. So here's the weird property. there are a whole bunch of processes. And everybody calls MPI receive, and then everybody calls MPI send. So that everybody can exchange data with everybody else. I mean, I'm exchanging data with my immediate neighbor, and my neighbor is exchanging with someone else, and so on. Right? Maybe it goes both directions, one at a time. If we all call MPI receive, and then we all call MPI send, we'll never call MPI send. Because once we call MPI receive, we have to wait inside the call to MPI receive until the data shows up from the other process. And because nobody is calling MPI send yet, because they're all waiting on MPI receive, then the thing freezes up, and then eventually it'll time out and crash. Right? So that's no good. So we reject everybody call MPI receive and then everybody call MPI send. That's guaranteed to fail. And by the way, that's good. You know why that's good? Because if it's guaranteed to fail, will you choose to do it? Only the once, right? You'll learn your lesson. All right, so let's do it the other way around. Everybody calls MPI send, and then everybody calls MPI receive. So that one's actually a lot worse. That one works sometimes. And I guarantee sometimes is worse than always. And I have a story for that. Unfortunately, we don't have time to tell it. But I have a lovely story of a real life experience where that sort of screwed everything up because that approach had always worked before and suddenly failed. Anyway, so the problem with MPI send, everybody calling MPI send and then everybody calling MPI receive, and the standard, the MPI standard speaks to says that is up to the nth number. So on many MPI systems, if you do that, if the messages are small, and I'm carefully not defining that, if the messages are small, it'll work fine. But if the messages are big, and I'm carefully not defining that either, then it'll freeze up because there isn't enough room to put all the message data. So everything crashes. And you can't, it's very hard to know in advance how big is. So everybody calls MPI send, then everybody calls MPI receive, only works some of the time. And what you could do is have half of us call MPI send and half of us call MPI receive. And then once that's done, switch roles and have the other half do the other thing, right? That would work, but especially when you have odd numbers of processes, it gets to be a lot of trouble to figure out how to make that work correctly. And especially if you have odd numbers of processes in 3 different directions. Ugh. All right. Okay, I already said all that. Good. Okay. So the MPI people are very nice. They provided us with a super duper thing called MPI send receive, which is, in principle, everybody is sending and receiving at the same time. That's not really what happens under the covers necessarily. But from the perspective of the programmer who's using it, we can think of it that way. And whatever magic happens under the covers, the MPI implementation will handle that for us. It's not our problem. Okay? So the advantage of this is when we're doing a transport problem and we need to move data from here to here, but there's also data coming in here, right? So the fluid is flowing this way, right? So there's data coming in here, and also I'm putting data out there, and then I'm putting data out there. We can pretend that's really what's going on by using MPI send receive, right? And all the data flows properly. So what does that look like? Let's say we're sending all the data, I gotta do this, okay, here, westward, right, to my left, okay? So we have a westward send buffer. That's coming from the process on the east. And then how much of it is and what its data type is. And who is on my west, right? And then a tag for that. We have a westward receive buffer, the stuff that's coming in from over there, right? The westward send buffer is going to that one from me. The westward receive buffer is getting stuff coming in from there, right? Which is coming from my east neighbor. They're sending stuff to me, right? And all that other stuff. And I had to create some kind of communicator using MPI card shift and all that other stuff. Okay. So the beauty of that is this one is sending to me while I'm sending to that. So all the data moves in the right direction. Am I out of time?
1:30.
Okay, let me do it real quick. We talked about that. And I just want to show you something that I think is fascinating. Now, in principle, here's what's happening, right? We're moving information here and here, right? the information representing what's happening on the edge of this one, which will go into the ghost boundary of that one. So this is really what's happening. Here's a process, here's a process, here's a process. They have the data they're calculating in their ghost zones. The data that's calculated here is going to the ghost zones of this one. The data that's calculated here is going to the ghost zones of that one. Okay? But that's not really what you do. That would be too easy. No, what you really do is you have what we call buffers. A buffer is a temporary place in memory to put stuff until you don't need it anymore. So we copy the data from here into this buffer, and then we MPI send it into this process's buffer. This is my send buffer here. This is their receive buffer. In the meantime, I've copied this stuff into here. This process copied this stuff into this buffer, and then sent it to this one, which gets copied over to there. That's actually what happens. Now, notice what a big pain this is to do. This is not fun, but it'll run fast and get you the right answer if you do it reasonably bug-free. Okay? Now, what if the set of things around what you're calculating needs to do corners and such? Well, it turns out that you can solve that problem super trivially by just copying in even the stuff here and here into this buffer. And then when you copy it out of here, it even goes here and here. And I once did this with colored pencils to convince myself that this was true. And I did it in 2D, but I'm convinced it works in 3D. If you do that, and you do it east-west, north-south, up-down, at the end of all that, everything is in the right place. So that's a lovely outcome. And I think that's it. Oh, that's it. Yay. All right, we're done. Wow, I did it. I was only like 5 minutes over. Okay, questions from TV land or here in the room? Okay, thank you, everyone, and we will convene again. I believe it's next week, isn't it? Yes. All right, so we'll see you next week.